Hello class, today we're going to talk about how we can use the sampling distribution to test claims that are being made about an average. And we're going to see the type of conditional logic that is used when we test these claims. So for example, a classic rock radio station claims to play an average of 50 minutes of music every 1 hour time slot. All right, that doesn't mean that they play exactly 50 minutes for every 1 hour time slots. In some slots, they might play 49 minutes. In others, they might play 52 minutes, etc. But they should average out to 50. That's what the station is claiming. However, they seem to play an awful lot of commercials. So I'm getting suspicious. I'm betting that it's actually less than 50 minutes. They seem to play an awful lot of commercials. To investigate the station's claim, you, or I, randomly collect 12 different 1 hour time slots during the next week and record how many minutes of music the station plays in each of those time slots. All right, so I tune in for 12 various 1 hour time slots. Here are the data. All right, in the first one that I recorded, there was 44 minutes of music played. In the second one, there was 49 minutes of music played. In the third time slot, they played 45 minutes, etc. We got a few that are above 50, one that's on 50. My average is 47.9. Okay, so was the station lying? I don't know yet. If the average had been 20 minutes, then we can be pretty clear that the station is lying. But with 47.9, it's still possible that the true average is 50. We don't know yet. We're going to have to do some serious statistical analysis to be able to rule out the possibility that they do average 50 minutes per every 1 hour time slot. All right, so to do this, all right, when we work on this, let me get my pen going here. We're going to make use of the sampling distribution. We're going to make use of the sampling distribution. We're going to assume initially that the radio station is telling the truth, that the average of all of those 1 hour time slots has 50 minutes of music playing on average when we look at the entire population of 1 hour time slots. All right, and so if that's true of the whole population, then that's also going to be the average of our sampling distribution. This is our sampling distribution. Now remember that, I'm going to go ahead and give us our standard error. Our standard error is going to be 0.78. I'm going to show you guys how I got that towards the end. If our standard error is 0.78, then if we go over 2 standard errors, all right, that's going over 1. I'll go over 1 more. That's going to bring us to 48.44. And if I go over 2 to the right, that's going to put me at 51.56. All right, now according to the empirical rule, if this station is right and the true average is 50, then 95% of my samples, not 95% of my samples, 95% of all possible samples, 95% of all possible samples will have an average between 48.44 and 51.56. And so in other words, there's a less than a 5% chance that if I were to take a look at one sample, there's a less than a 5% chance that that one sample would be either less than 48.44 or greater than 51.56. All right, because there's a 95% chance that it'll be between 48.44 and 51.56. This is just making use of basic conditional logic. My example here is actually inspired by my initial loathing of the child actor from my generation named Frankie Muniz. Now my initial loathing kind of turned into a little bit of respect. And that's because you guys may not have ever heard of him because he stopped acting. All right, he made his millions as a child actor and then said, "I'm good." And if that happened to me, I would do the exact same thing. All right, and so this is going to give me. It's the same thing with Macaulay Culkin from Home Alone, by the way, as well. All right, those guys know how to do it. You make your millions before you're 20, and then you relax for the rest of life. All right, so what I'm telling you is that if I were a millionaire, then I would not go to work. All right, this is true. We have to accept this. All right. Now, and it's this entire compound statement is true. All right. Now, I'm doing this video. You guys have to listen to me. So evidently, I do go to work. So if I am going to work, then therefore we can conclude I'm not a millionaire. All right, so this is just a basic syllogism in conditional logic. It takes the form of this. If we assume this statement is true, that if P is true, then Q is true, and yet we know that Q is not true, then we therefore know that P can't be true as well. All right. If we know that if P were true, then Q would also be true, but Q is not true, then we know that P must also not be true. And that's just what I did right here. Now we're going to see another example of that, but this is going to be a little bit more relevant to statistics. All right. Let's say the probability of winning the Powerball is a 5% chance. If that's the probability of winning the Powerball, okay, if that actually is the probability of winning the Powerball, and then I enter, then for all intents and purposes, I won't win. But then lo and behold, I do win the Powerball, if only. But then I wouldn't be going to work, right? Okay, but I do win the Powerball. What do we conclude then? We would conclude, using the same logic that we did before, that the probability of winning the Powerball was not 5%. It was something higher, and that's why I won the Powerball. All right. If P, then Q. However, Q was false. I did win it, and therefore P was false. The probability was not 5%, but something higher. Now, obviously, in this case, because we have some elements of probability, it's going to complicate the syllogism a little bit. All right, so it's actually going to look like this. I likely won't win, but I do win. Therefore, either the probability was not 5%, but something higher, or something very rare happened. Okay, we have to accept one of these conclusions, though. Okay, so how does that shake out here? So just as a reminder, if we believe the rock station, then the true average is 50. The standard error is 0.78. This lower bound is 48.44. All right, and the upper bound was 51.56. All right, according to the empirical rule, if the radio station's telling the truth, then there is a less than a 5% chance of me getting an average that's either less than 48.44 or greater than 51.56, because 95% of those sample averages will be between 48.44 and 51.56. Now my average was 47.9. All right, 47.9. Therefore, this is how the syllogism would shake out. All right, if the true average is 50, then the probability of me getting a sample average that's either less than 48.44 or greater than 51.56 is equal to 5%. If that probability is equal to 5%, then my average likely won't be less than 48.6 or greater than 51.4. But my average was less than 48.6. It was 47.9. All right. So therefore, this probability was not 5%. All right. It was something greater than 5%, and that's why I was able to get that average that was less than 48.6. All right. Either it's greater than 5%, or something very rare happened. Now, when we're doing these statistical analyses like this, we just throw out that option. All right. We do not consider, it's always possible a miracle happens, but we rule those miracles out. All right. So in other words, we have just ruled this statement right here has just invalidated this possibility. All right. And if it's invalidated that, all right, if that is not true, all right, then, all right, the true average is not 50. All right. Because we just said if the true average is 50, then that probability is equal to 5%. But we're now concluding that it's not equal to 5%, it's something greater. But if it's not equal to 5%, then the true average is not 50. So the true average is going to be something a little bit less than 50. And so we have therefore refuted, we've given there's strong probability to think that the true average is less than 50. All right. So that's really all there is to that. Now, I made use of the standard error being 0.78. I want to show you guys how I did that because I'm going to ask you to do the same thing in your assignment. So here's our data. Let me see if I can. Okay, that'll work. I'm going to have you guys go to this website. It's called the Standard Deviation Calculator. Just copy paste in the data. All right, and I had a 44 in here. Keep population clicked or checked and click calculate. No. All right, let me do this. Okay, so it gives you your standard deviation. It's 2.69. I think I rounded it to 2.7. Now we're going to say that's the population standard deviation. All right, there's more complexities to that, but we're not going to deal with those for right now. So our sample standard deviation was 2.70, and we're going to assume that that's our population standard deviation as well, 2.70. And so then all I did, I took that 2.70 and then divided that by the square root of our sample size, which is 12. All right, and that's how I got 0.78. So you'll be doing something similar in your work. But that's just using our formula, right? Remember the standard error formula is equal to, the standard error is the standard deviation of the whole sampling distribution. It's equal to the population standard deviation divided by the square root of the sample size.